Welcome to Smarter Circuits. I'm your host, Ian Klein. You may notice that I'm not in my usual place. I'm in the Hephaestus fabrication shop. I'm not going to be doing a build video, but I have small children staying at my house for a while, and so in order to record sound without interruption, I'm recording here. Moving on. In this video, I'm going to cover some common low voltage and general electrical components, testing, and tools that will be invaluable to any do-it-yourselfer trying to circumnavigate the world of low voltage lighting systems and relays. Towards the end of the video, I'm going to demonstrate common testing functions of a multimeter, in case you don't need the low voltage information and just need to know how to use your meter for some simple troubleshooting. This will be a long video, so I'll break it into chapters for convenient reference. First, I want to give a little background on what led to this video as a way to illustrate that with the right knowledge, even something new and unfamiliar can be analyzed and understood with a little patience and guidance. You can skip this chapter, but it's pretty interesting if you've been around these systems or like unusual electrical things. Last month, I was contacted by a couple in Louisiana who recently had some trouble with a section of their home controlled by a low voltage lighting system. The trouble came after an electrician came to upgrade their switches to a smart system. During the installation of the switches, the electrician did not realize that one of the legs was meant to be a constant power to a relay box, and so disabled the system when a certain bathroom light was turned off. I'll get more into that in a moment. I want to start with the first image that was sent to me. As you can see, this is not the normal system I'm used to talking about. In fact, it looks more like the system I have created now. See? This was a little bit jarring at first. I assumed that the switches at the wall were momentary and that these were paired up in a latching configuration, but later discovered that they are simply connected to toggle switches. In fact, some electrician along the way, in order to get continuous power to the other circuits in the wall, simply twisted the relay control wires together, turning some relays on permanently, and wired switches up to the now constantly powered circuits. This is bad, of course, for a multitude of reasons, but not really dangerous in this system because these relays are more than adequate to take the abuse. I'll explain. Keen-eyed viewers will undoubtedly have noticed that the relays in this image are the same type as this one from my previous videos explaining relays. This is a very reliable component under normal operating conditions and will likely last many years. In this instance, some of these relays are powered all the time and some are controlled, but will never power anything if another switch in the house is turned off. No one wants combination lock switches when they need to pee, so this had to be remedied. After doing a little tracing work and having a happy accident involving a crossed neutral tripping an unidentified breaker, the homeowners were able to figure out which wire needed to be connected directly in order to restore the original system configuration. This was after an estimate from a different electrician of over $6,000 to run all new wiring. I was not familiar with this specific home, and I had not seen a system that used these relays in such a direct way. I had only a few hours of time over a Discord video chat with the homeowners, and we were still able to trace the issue with only a little investigative work. It's a pity the first electrician missed this when he tried to assess the system. But what's the point of all this? While I was talking to these homeowners, I had a minor revelation. There is a minimal toolkit of items and knowledge that might come in handy to identify how nearly any electrical system works, even if you've never seen it before. The most common components, and some uncommon ones, are uniquely identifiable, and knowing what they are used for in the first place might help build an understanding of what can or should be done with a malfunctioning system. Much of what I'm about to discuss I've covered in previous videos, so I apologize if any of this information is redundant, but I wanted to try to create a short guide to these components all in one place for easy reference. I hope this is helpful and eases the minds of anyone who might be sitting in the dark right now desperately trying to figure out how to get the lights back on. Oh, one more quick note. I am not the fastest to respond to comments. If you have an urgent question, please email me at smartercircuits@gmail.com, or you can join my Discord link below. I try to help where I can, but I also want to remind everyone that I am not a certified electrician. I'm just a bit handy. Always check and recheck your sources, and if you don't know what safety measures to take, don't do the thing you're thinking about doing until you talk to a professional. That being said, I'm also offering my consulting services for anyone who requires them, with the understanding that I'm not a certified electrician, so I can offer advice and tell you what I know, but you make repairs and upgrades at your own risk, as most DIY homeowners do. Okay, here we go. Common electrical information and components you might find in any residential system in the US. There are parallels in the UK and across the globe, but I'm not familiar with enough of them to speak confidently about them or their ratings. So if you're viewing this from outside the States, please make sure to follow up with material from your local building and electrical council or agency as well. Many of these concepts will still apply generally because no matter how much technology advances, it will never change the way electricity works from a fundamental or practical perspective. A switch will always be a switch at the point where it interrupts a circuit. Before we talk about specific electrical components, let's talk about AC and DC briefly. In the interest of keeping this comprehensive but practical, I'm going to leave the explanation of motive electrons, magnetic field flux, and electron charge gradients to Electroboom and Veritasium, both fantastic science channels that I highly recommend to any hobbyist playing with electricity. For our purposes, these are the things you need to understand. First, you cannot mix AC and DC circuits. That is one reason we use relays. You also cannot, unless specifically instructed by a manufacturer, combine power sources. For instance, you cannot use two 12-volt DC power supplies to increase your current. The way most power supplies work, they will not be able to synchronize, and this will cause critical failures and potentially fires. Don't do it. AC power sources will usually be from the same main line in a home, but you still don't want to combine these in ways not specified by a manufacturer because you may be backfeeding a line. I want to elaborate on that for a moment because we'll be talking about generators, batteries, and solar systems at some point on this channel. In an AC system with a backup power supply, you will always see a device that prevents the grid main from being turned on at the same time as the tap from the backup. The reason for this is that if the power company's line is damaged a mile away and you turn on your generator or battery bank, you could potentially power that previously isolated section of the grid, and the line technicians working on the problem would not know the lines are live. Even if the damaged section is miles from you, the transmission infrastructure in place will do its job and carry your power as far as it can in the most efficient way possible, which could be deadly. You could also do this same sort of thing locally in your home by combining the circuits separated by two breakers so that when one is turned off, the circuit it controls is still hot. For this and many other reasons, do not combine power sources or hot wires in any situation. Okay, back to the fundamentals. DC is direct current and travels, you guessed it, in one direction. Don't spam the comments section, I'm keeping the surface level here. DC is most commonly used in small electronics, and in the context of lighting systems it is commonly used for control circuit power. I'll talk more about this in a little while. Most DC components will not work or will fail catastrophically if you do not wire the ground and hot correctly. AC is alternating current, which is a little misleading to the practical understanding of it. You still have a hot wire where your switches belong. In fact, in an AC circuit, this is even more important because you may end up with a live circuit even if your switch is turned off if you don't switch the hot. Again, no trolling. It's the safest advice. Let's talk about the polarity of an AC circuit for a second. Many AC circuits will operate with no preference to polarity, meaning the neutral and hot being swapped. So you must always be consciously aware of the correct wiring or something could go unnoticed until there is a failure or worse. In summary, whether you're working with AC or DC, polarity matters. Pay attention. If you don't know what should go where, don't do the thing. For residential AC wiring, most codes specify that the neutral wire be white and the hot wire be black, in all the places I'm familiar with. In the US, the larger blade on an outlet is the neutral and the narrower one is hot. I will cover some more complex plug types later or in another video depending on how long this runs. Now, I want to cover conversion of AC and DC to one another. There are several devices designed to do this, but they mostly make use of the two simple things you see here. This is a transformer, and this is a full bridge rectifier. I can't say that without hearing Electroboom's voice in my head. The full bridge rectifier is made up of diodes wired in such a way that when you pass alternating current into it, it separates the current flowing in one direction from the other and creates direct current. A diode is capable of doing this to some extent by itself, but the configuration in this rectifier does more to smooth the current. For more detailed information on this, I'll link to Electroboom's video on the subject. He's way more charismatic than I am anyway. If you see one of these in your system, chances are it is connected after one of these, the humble transformer. There are many types of transformers, but the one you'll most likely encounter in the low voltage world is this one, the step-down transformer. This particular one takes a 120 volt supply and steps it down to a 24 volt output. There are two important things to remember about a transformer. One, It acts sort of like gears, converting speed and power. When you step down voltage, you get more current. When you step voltage up, you get less current. The other thing to note is that, like the gear example, you can operate this device in either direction. Meaning, if you were to inadvertently power the low side of this transformer, it will happily step the voltage up and supply it to the lines connected to the high side. In systems with many circuits, more than one transformer may be in use, and if you cross the hot from one with the ground from another at a switch plate, you could potentially end up with live wires where you don't want them. I covered this in the section on using more than one power source for a circuit. Don't do it. Now, let's talk about when, where, and why you will see these two items. In low voltage lighting systems, these transformers are used to power the relays and will be delivering AC power, usually 24 volts, through the wall switches and to the relay coils. This is true in momentary or toggle switches. In older systems, like the one originally found in my house, the most common used relays are these solenoid relays, which I'll cover in more detail shortly. These use AC-powered coils to push or pull the circuit on or off. These relays, like the ones in the Louisiana system, are powered by DC, and you'll likely find one of these rectifiers connected after the transformer to convert the AC output to DC. If for some reason you see a transformer and one of these, but they aren't near your relays, you can bet there's relays somewhere that look like these. In some rare cases, these relays can be found at the fixture, but this isn't normally done for two reasons. One, they are harder to access and replace if necessary, and two, they emit an audible click that can be mistaken for an arcing circuit. This last point will help you determine if this is the case, however, as you'll be able to hear the relay when you turn the fixture on or off. If you're screaming at me right now that you can't turn the thing on or off to determine if your relay is in the fixture or not, rest assured it's probably not. Keep looking closer to where the power comes into the building. That brings me to another topic that isn't as much about these components themselves as about where you should find them. You will typically find all of these devices closest to the place the power enters your building, not just because this is convenient, but it also limits the length of certain wires necessary to make the system work and is often in a central location for easy wire management anyway. Attics and basements. Some unlucky folks will have relay boxes in shallow attic crawl spaces, and my hat's off to you poor souls. May your fingers be nimble and your wires not cross. Transformers can be found atop breaker boxes inside relay panels or haphazardly mounted to rafters. They're quite safe under normal operating conditions. They're even pretty good at taking some abuse, but it'll cost you on your utility bill if they're overloaded, as well as needing to be replaced faster. An extra note about transformers. They are used for other things in some instances. Example, here I have two transformers. I assumed that my system had maybe a few too many relays recommended for this transformer, so they added the dinky one, as though adding another one of these big guys wasn't something they'd do on a whim for the extra $3. The truth of the matter is that when I disconnected both transformers, which I stand by as a safety measure in general, I inadvertently disabled my very old doorbell. This was easy to remedy, and it was obvious which transformer made the dinging possible versus possibly handling power to every switch in the house. Let's go back to our relays, starting with the old solenoid relays from the 1950s and on. These are interesting relays that I've gone into great detail on in another video, perhaps the one that led you here, but I'm going to point out the practical stuff. These relays have two coils, one to turn on the controlled circuit and one to turn it off. Each coil requires a separate power wire, and this is often the reason for failures. On this relay, this is the switched side that will have one wire coming from the circuit breaker panel and one going to the fixture or circuit being controlled. On the other side, there will be a common or ground wire and a wire for on and one for off. The colors can vary, but testing is fairly easy. I will cover techniques for testing the various components when I cover meters later in the video. The switches that accompanied these relays were mostly these rocker-style switches with very little travel and even less as people haphazardly painted over them. Some would stick over time, leaving the power on to the on or off coil in the solenoid and causing it to overheat and fuse. This will become a power vampire on the transformer, but it'll happily dissipate the excess as heat and wear itself down rather than catch your house on fire. So good on it. The relay will then either not flip the other direction, or it will flip the other direction and never return. Either way, you have a very pesky troubleshooting situation on your hands. Likely the reason I've acquired half my subscribers, I'd bet. Oftentimes, you can identify a bad relay by listening for a buzzing relay, which you may have a functional buzzing relay, but not for long. You can still get replacements for these relays for about $90, but there are alternatives too. These alternatives will depend on your needs, resources, and skills at times. I'll discuss the alternatives as we progress. One of them includes the next relay. This DC relay differs from the old solenoid relay in one important aspect. You must apply constant power to change the state. Now, crafty listeners will have noticed that I said change the state, not turn it on. This is because these relays can be wired to turn a circuit on when power is applied or when power is taken away. This is useful for a variety of things, including making a pair of these act like a solenoid relay. These relays have a standardized socket that always follows this diagram. You have a terminal pair for powering the coil, which changes which contacts are closed or open. When the coil is not powered, the terminals on the next level of the side with the coil power will be connected to the furthest pair of terminals. When power is applied to the coil, the same first terminals will be connected to the second set of terminals on the other side closer to the relay body. The pairs are independent of one another, meaning that the terminals on the left and the terminals on the right, not used for powering the coil, are not connected to each other in any way. A relay that stays on after power is applied only for a moment is called a latching relay, and you can make one out of two of these relays. This is possible because of the two independent circuits on either side. This isn't necessary in most cases because you can simply use a toggle switch, and even more advanced, you can use a relay with a momentary button to create a momentary press on a higher voltage circuit for something like a Shelly relay, so you can program what to do on a button press versus when a switch is on or off. I like this option because you can also program things like long versus short or single versus double presses, something I covered in my RF remote video. This is a rotary dial, obviously. In low voltage systems, these are really awesome and daunting at the same time. You can have as many switches as you want per relay in these systems, unlike most standard wiring, which requires special switches to have more than one, and having more than three is nearly impossible. This means you can do things like this, where you have a dial that routes the on and off output wires from the switch here to any one of 9 relays. It's a master control panel capable of controlling significant portions of the first and second floor, from 1954, something that still blows my mind. There are so many deeply awesome possibilities with these switch wires in these houses that I could go on for hours. Low voltage power distribution for ARM devices like Raspberry Pi, low bandwidth data signaling using boosted I2C serial communication for sensors, carrying house-wide audio signals, even just leaving them alone and using them for these switches is pretty awesome. Some people with these old master panels or switches may have lights in them. They will likely also have 4-wire solenoid relays and possibly an additional transformer or power supply for the lights in the switches. You can keep or bypass these during conversion, and if I ever get the chance to work on one or acquire old equipment, I'll do a video on how to keep the lights but update the system. Now that I've covered more or less all the basic components of a low voltage lighting system, let's look at how to test and trace things. The absolute best tool I've found for tracing unmarked wires is one of these. This is a Fox and Hound tester. This box emits a very weak radio frequency through the wire, and this uses a very weak antenna to pick up that tone. The result is that you need to nearly touch the side of the wire to hear the tone, allowing you to single out wires in a bundle like this. There are other ways of tracing these wires that involve simply turning things on and off or disconnecting them and seeing what changes. I won't walk you step by step through that process because it's something everyone will approach differently in different scenarios, but I can tell you to try matching the state of the thing you're troubleshooting. What I mean by that is that sometimes these old low voltage systems, the problem isn't that a light won't turn on, but one that won't turn off. In this instance, it may be very helpful to turn everything on and systematically turn things off to label them until you don't notice a change. In that case, don't assume it's the one you want. It may just be something you haven't seen change, but make a note of it and continue until you've identified everything. Keep meticulous records as though it was your greatest obsession. Know your system as though you're Scotty on the Enterprise, or Geordi if you're young enough. This is a multifunction electrical meter. It can measure voltage, current, resistance, and continuity, all the things that make circuits happen. Voltage is the how much, current is the how fast, Resistance is the how restricted, and continuity is the are we connected. There are a lot of useful calculators on the internet for different things, but for most of what you'll ever need to work out, these two things will help. Watts is amps times volts. Amps is watts divided by volts. This also means that volts is watts divided by amps, but that is rarely useful for what we're doing. The second thing is less commonly useful in low voltage because manufactured tolerances don't require you to know this, but it's still handy. When you're wiring multiple loads in series, the resistance is the sum of those resistances. When you're wiring multiple loads in parallel, the resistance is the sum of the reciprocal of all the resistances. This is especially useful in audio setups, which I'll probably get to doing videos on eventually. When testing any circuits, assume it's live and keep your fingers, and anything else you may be waving too close to something, away from exposed metal. If you are grounded anywhere and you touch a live wire, the circuit breaker will not save your life. I repeat, the circuit breaker is an asshole, it is not your friend. It has only interest in saving your precious wall wiring from thermal breakdown. It is not the thing that stops a circuit from killing you. That's a ground fault circuit interrupter, or GFCI. They make GFCI breakers, but even if you have one, don't field test it with your body. Some of the things you'll be doing to test circuits will feel like a kindergarten teacher once scolded you for trying, but we're adults now, so it's okay. There are things I will tell you that are dangerous if you do them incorrectly, so please, I cannot stress this enough, if you are not absolutely confident in your understanding of the situation, do not do the thing. Fear in great quantity can make us do stupid things. Without any fear, we can be equally stupid, so make sure you know what the danger is and take precautions necessary to stay safe. One reason I'm emphasizing this is that there is a scenario that I will describe where a meter was not necessary and may have even made things worse, but the testing technique was risky. While walking the homeowner I spoke to in Louisiana through their issue, we came upon the following scenario. There was an open switch box with 6 wires coming out, 5 black and 1 white. Using the meter, we determined that one of the wires was hot, even with the breaker turned off that was previously thought to control that section of the house. No other circuit was working in that area. To the right of this box was another with nothing but low voltage wires coming out, and that had originally gone to several toggle switches. Some of these low voltage pairs were twisted together and taped. Testing the hot with each of the other wires was not physically possible without having to hold some part of the wire in a precarious way. So I walked the homeowner through using an alligator clip jumper to test these wires. Much thought was given to this approach and the utmost caution was exercised, although I will also point out that being free from any grounding, the homeowner was quite safe even when the circuit was complete, for reasons that would lengthen this video significantly. Go watch Electroboom for that stuff. So now I'm going to go off script for a few minutes to talk about some hand tools, including how to use this multimeter to do various tests. Okay, so what I have here is a setup that is meant to emulate the same sort of situation that the homeowner in Louisiana ran into in his home. We have a toggle switch running to a solid state relay. That solid state relay switches the hot wire coming from the circuit breaker box and going to the outlets or light fixtures. We have the Benchtop power supply here is basically emulating the transformer and full bridge rectifier combination in that situation. This will be very similar to situations where you have these old solenoid relays, but I didn't want to have to set up an AC circuit for these. I think they can still be run on DC, but I'm not sure. Maybe I'll test that in another video. Okay, so first let's dive into some hand tools that are absolutely necessary if you're doing this sort of thing. Obviously, you're going to want a Phillips head and flathead screwdriver. Having a 1/4 inch or a little larger flathead and a number 2 Phillips is your best bet. Having a pair of these is okay, but I actually prefer actual wire strippers. These don't crush when you just strip wire off. I don't like stripping wire with these kind of clippers. It's not really what they're for. and they will always crush, versus this that has, you know, the 2-blade for cutting here. Don't get me wrong, I do it sometimes, especially when you're in a jam and you're working in a tight space and you just need something to get in there. The other thing that I want to recommend as far as simple hand tools, don't use this. You'll want to. These aren't even really great, in my opinion, in mechanical situations, because they're just sloppy devices. They mar, they bite. I usually use them for holding material that I'm doing something to, versus trying to undo bolts or that sort of thing with these, because it's just not what they're good at, in my opinion. Instead, I always have something like this. These are fantastic. The snub nose guys with no cutter. So many different ways these become useful. Realize that I'm like waving that in front of the camera there. I actually have a set of pliers that comes with, you know, all these little guys, and I use every one of these for their various little purposes. But if you're going to only have 2 things in your tool carry while you're doing things, it should be these 2 things, along with your screwdrivers, and then of course one of these guys. This is an outlet tester. This is a very new outlet. And so you can see here that it will just tell you what is wrong without having to take anything apart. Definitely recommend having one of these. I'm using it for this test just so that you can see when the circuit's lit up versus when it is not. And then, of course, your multimeter itself. Ooh, bump the camera. So let's go over the multimeter real quick. I've sort of brushed over this earlier in the video. This section is DC voltage. Each one of these is the accuracy or range, more to the point, the range of the display, the test that it's doing. So typically when you're using it in the low voltage systems, you're going to be anywhere between 5 and 24 volts, sometimes as high as 36. So you'll want to put it on the 20 on your meter. This little indicator here means DC. That is an international electrical symbol, as is the little squiggly line, which means AC. All of these are. V is for voltage, so this is the volts AC section, and you will normally have that in the 200 position for testing 120 or 240 volt, which if you're messing with 240 volt, you probably know all of this. This is not on all meters. This is for a thermistor so that I can do temperature readings. Again, this is not on all meters. This is the frequency and function section of my meter. This is on most meters. This is the resistance testing, which I'm not going to really demonstrate here because you probably won't need to do that for most of the things that you'll need to do. If you do want me to do a more comprehensive video on the function, the diode test, the amperage tests, that sort of thing, let me know in the comments and I'll do another video on the rest of the functions of this meter. But this is really just for general electrical and low voltage lighting system information. So the A, as I just kind of mentioned, A here in the DC range, and then here in the AC range, the A is for amperage. So that is your current testing. You can also test for continuity. This is the other thing that this will be useful for you. Let me turn it back on. It went to sleep. When you're doing stuff like this, you can use it to see if something is actually broken or not. But for the most part, like I said, you'll be doing this in the volts DC and the volts AC. So let's go ahead and start looking at that now. I have it in the AC position, and this is the situation that I have. Let's assume for a moment that you're not getting power here, and you want to know whether or not this relay is engaged because you don't know which switch it goes to or what the state of that switch is. So in order to do that, first you would want to test the power coming into the system wherever you can. When you're testing AC, the order of the leads doesn't matter. It's AC. So you just probe the neutral and probe the hot, and you should get about 115 to 120 volts, right? Well, probably 110 to 120 volts, which is why they call it 110. So Obviously I have power going there, I just don't have power going to my outlet. So the next thing that I would want to do is see if the power has made it to the relay. Don't skip this bit. So go to the neutral and then go to where the power should be in and make sure that your line is good. Obviously ours is. If there was a break in that little wire, I'd be pretty surprised. And then you can test after if you think the relay should be on. So I go to my neutral and I test here, and I don't have my voltage. There's a tiny bit, and that is one of the reasons why you're able to tell if there is an open neutral, and also one of the reasons why AC is sort of dangerous if you don't concern yourself with polarity, because there will always be a minute amount of voltage. And if you create a situation, or if you close the circuit with a ground, you will get the full brunt of that hot wire. So I'm going to turn the relay on now, and I should be able to test this and get power. Uh-oh, wait a minute. Is the relay on? Oh, haha, see? Very good. So now, and I could have gone over here and I could have tested this and said, okay, am I getting voltage? I'm not getting voltage. So let's turn that on. And now if I test it, well, what do you know? There we go. What do you know? I'm getting about 9 volts. Now, if I swap these leads, the worst thing that's going to happen in this scenario is that I'm going to get a negative number. Some components, especially if you're looking at a combination of components, and by components I mean resistors, etc., some components will measure a different voltage in the opposite direction or no voltage for various reasons I'm not going to get into. So that's why you do want to make sure that your polarity is right. If you're just looking to see if voltage is present, it's not as big of a deal, especially at these lower voltages. So let me kick back over to the AC side here. And now, of course, I mean, you can tell because the light's on. But if that were tripped, then I would want to know, oops, bump the camera again. I would want to know if there was power here, and there is, right? And this isn't going to tell me that. Of course, if I reset my breaker, then there it goes. Okay, my camera cut out on me, so sorry about that little jump there, but that pretty much covers it for the meter and for testing these circuits. If you want to see me cover more hand tools or do a more comprehensive video on the meter, let me know in the comments. And now back to me. I do hope you enjoyed the video, and of course if you did enjoy it and haven't already done so, please do subscribe to the channel. If you want to know what's going on between episodes, you can follow Smarter Circuits on Twitter @CircuitsSmarter, and if you'd like to help make more and better videos possible, consider becoming a patron on our Patreon page, linked below. Thanks for listening to me ramble, and I do hope you'll join me for future videos as I continue exploring smarter circuits.